Tell us what the word is.
Oh, for today? Okay,
Yeah.
I won't tell you. It's a good one.
I have 100% accuracy rate so far.
All right, today is Thursday, February 26th. We are finishing the AP style review of applications of differentiation. We are on the last problem. We only have part C left. Okay. Ooh, classic particle motion. Classic AP exam type problem.
You really like this problem.
You've never, yeah, I like them all.
All right, I'll write stuff down.
You've never been here before, welcome. This is what we do, we just go over AP problems, but we only have one left and then we'll get into packet, don't worry. So just
day one.
Just observe, Dalton, and just absorb. Okay, here we go, part C. We already did parts A and B. A second particle, Y, moves along the positive y-axis. So that its position at time t is given by this linear function. All right, so to go back, we had particle X that was moving along the x-axis. So we'll just kind of draw a picture here. There's my position of my particle X. And then now I have a second particle, Y, that's moving along the positive y-axis. Okay, so there's its position at time t. At any time greater than or equal to 0, the origin and the positions of the particle X and Y are vertices of a triangle. Okay, let's just sketch this out. So they're saying the origin and these positions would form a triangle. Find the rate of change of the area of the triangle at time t equals 1. So when I see that rate of change, I'm thinking derivative. And then instantaneous rate of change, I'll obviously plug in 1 once I find the derivative. Okay, so it's the rate of change of the area. So how do you find the area of a triangle? Geometry students? How do you find the area of a triangle?
1/2 times base.
Thank you. 1/2 times base.
Already doing better than
Base, which would be the position on the X particle, times height, which would be the position of the Y particle. Okay. We are given the equations for these positions of these functions after t amount of time, so let's go ahead and plug those in. So it's 1/2 5t cubed minus 9t squared plus 7 would be my X times 7t plus 3. So here's my area function in terms of time, which is good, because I want to find the rate of change with respect to time. 2 ways you could do this derivative. You could multiply everything out if you wanted to, or you could use product rule. That's with limits. I used product rule to find this derivative. I don't know if that would be easier or not. This is how I did it. It's not bad. So I essentially just brought out that 1/2.
Carson French, please report to the office. Carson French.
I don't know who that is. And then I have 2 factors here. So I'm just going to do product rule. So I have the first factor, 5t cubed minus 9t squared plus 7 times the derivative of the second, which is just 7. Plus second factor, 7t plus 3 times the derivative of the first factor, which would just be 15t squared minus 18t. Okay. Now, honestly, guys, I wouldn't go any further with the algebra because we want the instantaneous rate of change, so we have to plug in 1 for time. So if it's easier for you to just start plugging in 1 to everything, I think that'd probably be easier than trying to multiply this out, I guess. Is we're trying to find the rate of change after 1 second. So I'm just going to plug 1 in for all my t's, and then that's pretty easy to crunch that number. I'd have to look if this is on a calculator or no calculator part. I'm not sure off the top of my head. But we could do this math easily in our head. Oops. That would let me go off the page. Minus 18 Okay. So let's just practice doing this without our calculator. Here we have, obviously, 5 minus 9 plus 7. I gotta take that times 7. Plus 7 plus 3 times 15 minus 18. Okay. So 5 minus 9 plus 7 would be 3 times 7. We get 21 plus 10 times negative 3, negative 30. So that's negative 9 halves. I'm just running out of room. I do this all the time, this thing you taught me. The eraser with my hand. Like this. Yeah, I like it. Okay. Do you guys think you would have got that problem right? Yeah.
You should watch a YouTube video on how to use a smartphone.
I need to watch YouTube videos. Okay. I feel like I'm pretty good with it. I just
learn the shortcuts.
Yeah, you're right. Okay. So that's that finishes up derivatives. Now I found some old AP problems that are more on integrals, which is what we kind of did in chapter 4. Yes, welcome to the club. It is a fun time here. Okay.
Did you guys play Letter League after you played Wordle? Letter
Mm-mm.
League.
I don't know what that is.
You gotta guess the letter.
Instead of the word?
Yeah.
Oh, no, we didn't. I found this app on my computer that they could do just a bunch of Wordles.
Oh, what's it called?
Wordle Plus, I think.
You just paid for it.
No, it's free.
You shouldn't download that.
Mhm. I don't know if it would work on Chromebooks. It was on my Play Store thing. It was on this thing.
So we're gonna have to download that in.
Wait, let's look if it's on my
Yeah,
recents.
put it in a character.
It was on my Microsoft Store. Oh, let's go to my library. This Wordle Plus, or was it Wordle Game? It's one of these
Probably
two.
Wordle Plus. Let's try.
I think it was this one actually. And then you could go to practice mode. Oh, I don't want to go to the one of the day. No, this is practice. This isn't the one.
Oh, okay.
Practice, and then it just let them do it over and over and over again. But the Wordle, that was the one of the day.
Did you get that one?
We get this one?
No, did you get the Wordle?
Yeah.
Can we play one?
No.
Why not?
Because we got a calculus to do.
We did calculus this morning.
All right.
You got a free.
I'm really excited for this. This packet's going to be fun.
Is it like chocolate milk in that cup?
It's coffee. I'm a little traumatized from that milk yesterday. I was like, I don't think it's going to be like 8 years before I drink milk again.
Did you drink some?
That hurt my belly.
I couldn't chug it.
You did too. Yeah, you had more than I did. I mean, I didn't finish mine.
I didn't feel sick at all.
You
So
did
you're
it.
gonna give them the 5% on algebra.
I got a lot of air when I drank mine.
I was trying to drink mine, but the hole wasn't letting any out.
Yeah, you just like sprayed yours.
Yeah, I'd squeeze it and my sweatshirt stinks.
So
Yeah, milk is not good when it's old. Crusty. I don't even like milk really. I like it with Oreos and that's about it.
Or chunky milk.
Okay. Here we have a multiple choice type of problem. During an evacuation drill, people leave a building at a rate R of T, so we're given the derivative here, people per minute.
Jay Babel, please stop in the office. Jay Babel.
T is the number of minutes since the start of the drill. Selected values of R of T are shown in the table above. Use a Wright-Riemann sum with 3 subintervals and data from the table. What is the approximation of the number of people who leave the building during the first 15 minutes of the evacuation drill? Okay, so Wright-Riemann sum. Obviously, my 3 subintervals would be there from 0 to 5, 5 to 10, 10 to 15. So if I'm doing it in a Wright-Riemann sum, or I like to call it RAM, because the widths are all the same, my delta x here, 15 minus 0 over my 3 subintervals. My width of these are all 5. You could just do 5 times all the right-hand heights of that rectangle. Or maybe you could do each rectangle separately if you want to, but this would be quicker, I think. Okay, that one you guys could definitely do. We just got done doing that. I got B, 1,150. And remember, we're essentially calculating the area under that curve with rectangles because we were given the rate. So if I calculate the area underneath, that would tell me the accumulated amount.
Does that look like that,
I forget which order it goes in. Hold on, let me look it up. The first 30, I think, are no calculator.
Yeah.
Is that what I've been saying? I always get the order mixed up.
Yeah, so it's like chunking like all right now. I think it's like I threw it.
Here it is. Okay, so yep, the questions 1 through 30 is no calc.
So this was done on.
This is a no calc, so you would have had to calculate that in your head. That's what I'm saying. Like in free response, they kind of like let you leave your answer like that, but in multiple choice, you're gonna have to simplify things. Yeah. Yes, that's good to point out. This was on a no calculator part. So with this next one. Okay. Okay. I have a piecewise function here. They want me to find the definite integral from -1 to 1 of f of x dx. So I'm looking at my piecewise here and I see there's obviously like a break at 0. So if I want to find the area under the curve from -1 to 1, I'm going to have to do the area under the curve from -1 to 0. Yeah. I'm going to figure out what it is from -1 to 0. So that would obviously be like my x squared piece because that's for everything less than 0. And then I'll add it in the area from 0 to 1. And that would be my x curve. Okay. So that would be from -1 to 0. I would use this piece, x squared dx. From 0 to 1. That'd be the x piece. Okay. So you guys know how to evaluate definite integrals. Find the antiderivative. Fundamental theorem of calculus, part 1. Add 1 to the power. Divide by the new power. I'm going to write that as 1/3. My bounds would be 0 and -1. Plus, this would just be 1/2 x squared. Bounds of 1 and 0. Again, this would be a no calculator one. You don't have to be super neat with your work. Here we'd plug in 0 minus when I plug in -1 plus when I plug in 1 minus when I plug in 0. Okay, so if I were you, any of the 0 ones I kind of just like cross off. Like, right, those are obviously 0. So here I have positive 1/3 plus 1/2, which would give me 5/6 if you made common denominators there. 2/6 and 3/6. 5/6. A. Okay, not bad. Good antiderivative practice there. Next one. It saves the ink on my page. Nice. Here I have the graph of a derivative. shown. First derivative. It consists of a semicircle of radius 2 and 2 line segments. Ooh, this is kind of a weird one. If g of 0 is 1, what is g of 3? Okay, so since I'm given the graph of the derivative and I want to recover information about the function itself, I'm probably going to integrate. Okay, if I'm given information about the derivative and I want to recover information about the function itself, I'm thinking antiderivatives. So really what we're going to do here is we're going to find from 0 to 3 g prime. I'm not going to do any like differential here. But I know that the antiderivative of g prime would be g, and then plugging in the bounds 3 and 0, it's going to be g of 3 minus g of 0. And we know what g of 0 is, according to our graph here. G of 0 is 1. So basically what we're going to do is we're going to calculate this using our graph, what the area under the curve is from 0 to 3, and we can essentially solve for what g of 3 would be. Okay, so from 0 to 3, g prime, that's saying find the area under the curve from here to here. So we have a quarter of a circle, so it'd be 1/4 pi r squared, radius is 2, plus triangle 1/2 base times height. Okay, so here 2 squared is 4, 1/4, I get pi plus 2, 1. I wrote my work different, and I was like, where's this other plus 1 coming from? It's coming from here. Okay, so this is pi plus 1 is the area under the curve. Okay, so this right here, this area of the curve is the same as pi plus 1. So kind of combining the fundamental theorem of calculus, here's everything that we know. So I know, obviously, like I said, the antiderivative using the definite integrals would be the same as doing g of 3 minus g of 0. And they tell me what g of 0 is, and I'm trying to find g of 3. So now that I calculated the area under the curve, because that's what this means, now that I know what that is, I can algebraically solve for what g of 3 is, which would be pi plus 2. B, is that right? Yep. Okay, that kind of makes sense. Again, it's like a weird way of asking like that type of question. But it combines fundamental theorem of calculus, and it combines, obviously, definite integrals of area under the curve. There could have been different ways. I mean, you could have started with just like calculating the area under the curve. You're like, okay, here's what I know. Here's what I'm trying to find. Ooh, do we know how to do this one yet? Oh, yeah, we do. Sorry, I think I cut out a different one. Oh, these ones that you guys stink at. Remember these ones? I shouldn't say you guys. Some of you stink at them. Finding the derivatives of integrals. Fundamental theorem of calculus part 2. If you want to derive integrals, as long as this is a constant, e is a constant, that's fine. As long as that's a constant, the integral and the derivative are inverse operations. They just undo each other. And you plug this bound into the function itself. So the derivative of that would be the natural log of x cubed squared plus 1 chain rule times 3x squared. Okay, so looking at my options here, I see I have the 3x squared. So I'm like looking at these two options. And then I obviously have x to the 6th there. Oop, I almost forgot natural log. Natural log x to the 6th plus 1. C. Is that right? Yes, C. Okay. Ooh. This would be a calculator active problem here. And you actually do need your grapher for this. I'm going to get my Oh, I read it out loud. A particle moves along the x-axis. See how common these particles are? Responders. The velocity of the particle at time t is given by this velocity function. If the position of the particle is x equals 1 when the time is 2, what is the position of the particle when the time is 4? Okay. So this is kind of almost like that graphic one we did, where we're given the derivative, which is the velocity, and we're asked to recover information about the position. So we're thinking integrals. Okay, and again, those like connections between first derivative, second derivative, original function, that's really important. So if we're given information about the velocity and asked to recover information about the position, I'm thinking I want to anti-derive velocity because I know that gives me my position. Okay, there's like the connection. I haven't done anything really here, but that's what you're thinking in your head. And I'm probably going to integrate. All right, I'm given the position of the particle at 2 seconds. So I could rewrite this that x of 2, after 2 seconds, the position is 1. So since I'm given that information, I'm probably going to want that to be one of my bounds. Thinking ahead, because I'm going to have to get my position at time 2, and I want to know the position at time 4. So my bounds here are going to be 2 for my lower bound and 4. And once we actually do the antiderivative, you'll kind of see why. Okay. So I could actually like plug in the velocity function, but you don't need to because we're going to do this all in our calculator. Here's the connection we need to make, that the antiderivative of the velocity would be the position. And then fundamental theorem of calculus, I would do the position at 4 minus the position at 2. So here's again why we want to pick one of those bounds to be 2, is because we know what this position at 2 is. It's 1. Okay, so I'm going to calculate this integral. And I know it's equal to the position of 4 minus the position at 2. I know that antiderivative, or that integral, I should say, that integral is the same thing as that. So I'm going to go ahead and plug in the actual velocity. And anytime you're given a calculator, especially looking at your answers are all decimals, you're going to use your calculator to calculate this. Okay, so let's pull up my grapher here. Math 9 is how you get the definite integral. So we're going from 2 to 4 of that velocity function. There's 2 ways you could do this. You could obviously just type it right in here, or you could type it into your y equals and do like alpha y1. But I'm just going to go ahead and type it right in here. Make sure in your denominator you wrap parentheses around that t cubed. Obviously you have to use x plus 1. And we'll just do this in terms of x. Don't waste your time trying to do u sub or anything like that. If you're given your calculator, you use it to calculate those. Okay, so you should get like 0.3525, yada, yada, yada. So here's what we know. We know this is at 0.3525, yada, yada, yada. And that's the same as my position after 4 seconds minus 1.
Have to ring the bell. Maverick Schultz, please.
So to find the position after 4 seconds, we'd add 1 to that.
Also Casey Walker and Isaac Wheeler Bonilla.
So that'd be C. Okay. So again, kind of a weird way of asking that question, but you'll kind of see these patterns a lot where they give you information about the position, or give you information, I should say, about the derivative, ask about information about position, and so we're thinking of these connections, and we'll practice more. So I'm going to stop the recording. Fun stuff.